Hey, everybody. I'll give it just a couple more seconds here before we truly jump in. But just to kind of give you a sense of where we're headed today, today will take me about a half an hour, and my intention was to finish 1.5, but I kind of took my foot off the gas just a little bit. And today will really be kind of a recap and more of a revisiting of the last 2 days, just to kind of ensure that things are starting to stick or starting to make sense a little bit, because this does get a little, abstract when we're talking about these electron configurations and when we're talking about these orbital diagrams. So I'll take about a half hour today of your time, and then we'll let you free, and we'll catch you guys tomorrow. So let me give you a couple of announcements just in general. First thing, with AP Classroom, if you weren't able to finish that first assignment on AP Classroom, you may have noticed if you went back to AP Classroom, like the first assignment was posted like 3 times and it was all weird and it was all messed up. That's because this guy was trying to fix things and I wasn't successful. So there's a couple students that are having issues with accessing AP Classroom. I've been attempting to fix some things, and I've been emailing some people and trying to figure out what the heck's going on. I haven't quite gotten to the bottom of it just yet. Long story short, don't worry about AP Classroom for the near future, okay? I'm not doing anything with it tomorrow because until I can ensure that it works for everybody, I'm not going to use it and leave, a handful of students that just are having access issues in the dust. That doesn't make any sense. So I'm hoping it gets fixed in the near future. I don't know when that will be, but long story short, ignore AP Classroom for the near future until I tell you we're back on. And the other thing with AP Classroom is if you didn't finish that first assignment, when things are back up and running, I'll open up that first assignment back up to everybody. And if you're a person that wasn't able to submit it the first time, you can totally submit it then, and I won't mark it late at all because it's been a little bit of a headache for me this week with AP Classroom. So side note on that. The other thing you hopefully got this morning was an email from me telling you that homework topic 2 has now been moved to Monday for a due date. So if you're a person that hadn't started that yet, congratulations, you're welcome. It's due on Monday. And if you had submitted it already, please feel free to, given the next 2 classes, if you feel like things are making more sense and there's a couple questions you feel more confident on, you're more than welcome to obviously fix things, change things, and then resubmit it. The reason why I pushed it back is because tomorrow I have a video for you of me doing a lab, and that lab video walks through quite a few of the things on that homework assignment. So it should help a lot, okay? So normally if we were here, right, we would have already done that lab. If we were here in person, you guys would have done the lab that I'm showing you tomorrow. You would have done that in week 1. And then some of these concepts that showed up on homework topic 2 would have been covered that day. That didn't happen. So I kind of got ahead of myself just a little bit because I forgot that we didn't teach you some things in lab. So tomorrow I'll teach you a couple things in lab, and then hopefully the homework assignment makes a little bit more sense. And that is now due on Monday night by midnight, okay? A couple other things. Homework topic 3, which is HW Unit 1, topic 3 in the top corner of your paper. That third topic will be due next week, Thursday by midnight, assuming that I can stay on schedule with things. So I'm hoping that I can. That's obviously a week out, but if you wanted to start taking a peek at that, you're more than welcome to. There's a couple things you can answer on there right now, and there's some things on there that we haven't talked about yet. So certainly not everything on there is doable at the moment, but if you want to take a head start on that, you're more than welcome to. That'll be due next week, Thursday. All right, that's all I got. Let's get started. We're going to jump back into 1.5. I have a couple of intro questions for you guys to start it, and then we'll kind of continue on just a little bit today. But for those intro questions, find a margin or find like the back of one of these sheets and see if you can answer these 2 questions. I'd like you to write out the electron configuration for krypton, which is element number 36. And I would also like you to attempt to draw the orbital diagram for sulfide, which is S2-, element 16 with a 2- charge, okay? I'm gonna give you a couple minutes. You might be completely lost and just sit here for 2 minutes, but at least maybe think about it or look back and contemplate what I'm asking you to do, and then I'll jump in and I'm gonna reteach a lot of this with this intro, with these intro questions, okay? So try it, I'll shut up, come back in a minute or so. I'm going to go grab a drink. And then, sorry, what? Nothing? Okay, somebody unmuted, sorry. Yeah, so give this a shot. I'll be back in a minute or so, and then I'll give you the answers and we'll go through it. All right. If you're still contemplating it, feel free to kind of just keep an open ear and start, or keep chipping away at it if you need to. But let me kind of talk you through this. And again, I'm going to kind of reteach and revisit these two ways of representing electrons. So over the last 2 days, I've introduced the quantum mechanical model of the atom. And again, this is a model that is getting away from electrons existing in these shells, or these electrons existing in orbits or clouds, or whatever you want to say. And this new model, this quantum mechanical model, is now putting...
Why did you do your comp essay like the day it was due? Like,
somebody's not muted. All right, anyway. So with that, these orbitals are three-dimensional regions of space, okay? They are, again, the shapes that I had on your note sheet were graphs, more or less, right? And the shaded region or the shaded shape of those things were where, with 99% confidence, that's where we would find the electron in that specific orbital. So with that said, or with this new model, we need ways of representing the electrons, or we need ways of showing where all of the electrons are, which orbitals they are in, and the order the electrons are in, okay? So that comes to these two things right here. Electron configurations and orbital diagrams. These are two ways of showing the exact same thing. We're going to go through both of them. Again, I taught them kind of yesterday a little bit more, but let's start with the first one. We want an electron configuration for krypton, okay? Krypton is element 36. It has 36 electrons. So what I'm really asking you to do here is give me the shorthand notation of those 36 electrons and the orbitals they exist in, okay? I'm going to go back in my presentation to that periodic table slide. Okay. So on this slide, yesterday in that video, I walked you through kind of how to count the electrons, right? In this atom, we want 36. So I'm going to add them one at a time using the periodic table. I have them numbered sort of, kind of, on this slide, but I start with electron number 1, right? When you use the periodic table for this type of problem, essentially each little box or each little element box represents 1 electron. So the very first 2 electrons are the boxes of hydrogen and helium. Those electrons are in the s block, and they're in the first row. That orbital then is 1 for the row and s for the block that those first 2 electrons exist in. I then use the superscript 2, which represents the fact that the 1s orbital has 2 electrons in it, okay? I keep going. I have way more than 2 electrons in my atom. I need to get to 36. So I've got to keep going until I have a total of 36 added. So the 3rd and 4th electrons are right here. They are also in the s block. This time it's in row 2. So the next orbital I have is 2s, and I use the superscript 2 to represent the 2 electrons that are in that orbital. I keep going. Electrons 5 through 10 are now in the p block. So this is a p orbital. This is row 2. So this is called a 2p set of orbitals. Remember, p orbitals come in sets of 3. If I have 3 orbitals in a set of p orbitals, each orbital can hold 2 electrons. That means that I have 1, 2, 3, 4, 5, 6 electrons that can fit. Coincidentally, the p block is 6 elements wide because that represents the 6 electrons that are in that set of orbitals. I keep going. I'm now on electrons 11 and 12. They are over here on the left-hand side. I'm in the 3rd row. This is an s block, so it's 3s. And again, s orbitals come in sets of 1. That's going to be 2 electrons. I keep going. I jump all the way across to p. Again, electrons 13 through 18 are in a p orbital or a set of p orbitals. This is row 3, so I call this 3p. And that can hold 6 electrons because, again, it's a set of 3. Each orbital holds 2, total of 6. I'm not done. I still need more. I'm only halfway there. I go to electron 19 and 20. They're in the 4th row. S block, 4s. And this is going to hold 2 electrons again because s orbitals only come in sets of 1. I now get to electrons 21 through 30, which are going to be in the d block. Now, the first time we see d orbitals show up is in row 4. But the energy level starts at 3 for D, okay? So this isn't 4D, it's actually 3D. Let me explain a little further. S and P orbitals, the energy level matches the row number. So if you are in row 6, it is 6s, it is 6p. If you are in the d orbitals, the energy level of d orbitals is 1 less than the row number, okay? The other way that I remember this is that s orbitals start in energy level 1, p orbitals start in energy level 2, d orbitals start in energy level 3. So the first time that I see a d orbital in my configuration, it is 3d, even though it's in the 4th row, okay? D orbitals, these come in sets of 5. I have 5 orbitals to fill. Each orbital holds 2 electrons. I can add 10 electrons to my set of d orbitals. So I have 3d with a 10 as the superscript. The 10 is the electrons. Last but not least, I need electrons 31 through 36 to be added. I'm back in the p block. I'm in row 4. So I'm going to finish it with 4p6. Okay? So in total, I have 36 electrons. If I add up all of the superscripts, 2 plus 2 plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36. I have all of my electrons added. This is the appropriate order that they are added. This is the order of the orbitals as you go through and add electrons to make these atoms, okay? I'm going to give you a second way of memorizing this order. If you feel comfortable with the periodic table method, the method I just kind of showed you with like using the blocks, right? S, P, D, F blocks on the periodic table and kind of counting as you go using the periodic table, awesome. It totally works and you can use it. But some of you are going to prefer this over that. So let me give you a second way of doing this. Find a spot somewhere in a margin or on the back of a page and draw this exactly as I'm drawing it. And this is a second way of memorizing or showing the order of the electrons. I'm going to write out all of the orbitals in a very specific pattern, okay? 1s, 2s, 3s, 4, that's too close. Whoa. Don't mind me, I just work here. 4s, 5s, 6s, and 7s, okay? Now I'm going to write out all the p orbitals, and I'm going to start in row 2. 2p, 3p, 4p, 5p, 6p, and 7p. Now I'm going to write out all the d orbitals, starting in row 3. 3d, is that a chat? No, it's not a chat, okay. 4d, 5d, and 6d. Now I'll write out all of the f orbitals, starting in row 4. 4f and 5f. There are 4 rows of d orbitals on the periodic table. There are only 2 rows of f orbitals on the periodic table. If you can write out this pattern, what you then can do is make some arrows to figure out the order of the orbitals. 1s is the first orbital. 2s is the second. 2p, 3s. 3p, 4s. 3d, 4p, 5s. 4d, 5p, 6s. 4f, 5d, 6p, 7s. 5f, 6d, 7p. This is the order of the orbitals for every single element on the entirety of the periodic table, all the way through element 118. You can figure out this order by using the periodic table like I showed you yesterday and I just reviewed today. But if you prefer this, if you can draw this and recreate this, the order is right in front of you. All you need to do is follow the arrows from tail to head as you go down, okay? Again, you start way up here, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, so on and so forth, okay? I don't care which one you use. I don't care which method works for you better. It doesn't really matter. What does matter is that you are able somehow, some way to determine the order of the orbitals. You are responsible for that. So if you prefer the periodic table, like I taught you yesterday, great. If this works for you, great. One of them hopefully does the trick. Okay, that was very long-winded, and that was only the first part of what I had for you, but let me go back to the problems and finish this up. All right, so I wrote out the electron configuration for krypton on the other slide, but there's another way we can do this. We can also abbreviate those electron configurations by using the noble gas from the previous row, if you remember that from yesterday too. So what I had was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. Okay, that's what I wrote on the other slide. You can abbreviate it. The previous noble gas prior to krypton is argon. Argon is represented by these 18 electrons right there. Instead of writing all of that out, I could bracket argon and then just continue after that point. 4s2, 3d10, or b6. This is also correct, okay? If you prefer to abbreviate those, that's perfectly fine. The only thing that I don't ask that you do is, krypton is a noble gas, right? I won't accept this. I'm not going to accept that. You didn't show me a darn thing. Okay. All right, the next one. The orbital diagram of sulfide. Sulfide, or sulfur 2- is 18 electrons total. Sulfur as a neutral atom has 16. Sulfide with a 2- charge, it's gained 2 electrons at that point. So we have 18 electrons to represent in our orbital diagram. The diagram means picture. A picture is going to imply that we have these platforms of the orbitals. The order is the same. The way we represent it is different. And it's going to look like this. The reason why I kind of have it like a staircase, or the reason why it goes up as we go, it's implying that the energy of the next orbital is higher than the previous orbital. Okay? So each platform is one orbital. And now I'm going to add my 18 electrons and fill them up as I go. The electrons I am representing as, I wanted red. The electrons are half arrows, okay? Each half arrow is either pointing upward or downward, and that's talking about spin. This is the Pauli exclusion principle. Don't worry about that title. Long story short, if 2 electrons are in the same orbital, or in other words, occupying the same space, they must be spinning in opposite directions so that they can coexist, so to speak. So one is up, one is down. Each arrow is an electron. This orbital is filled, and I keep on going. I get to 2p, and now when I add these electrons, I first add them one at a time, and then I pair them up if I need to add more, which in this case we do. We have 18 total to add. I've got 2, 4, 6, 8, 10 at the moment. 12, 18. And this is the orbital diagram for sulfide. Okay? Now, my intention wasn't to take that long. The first hour I did this, but that's how long it took. So that's why I'm cutting class just a smidge short today. Sorry, you can see yourselves in the background. There we go. But anyway, I'm hoping that sort of makes sense. If you have questions or if something is just not clicking, right, please hang out after class. I'll answer some questions if need be, and I'll certainly help you. I'm not going to leave you hanging. Once this stuff clicks, it's not too bad. I said that a couple days ago, but somewhere along the line of teaching this stuff, it's got to click for you. And it might take just a one-on-one conversation to hopefully kind of have something settle in your brain. Okay. All right. So let's do a couple.
Mr.
Yeah, sorry.
I have a question.
Go for it.
Are we on a specific page right now, or are we just like writing stuff down?
We were just writing stuff down randomly, probably on the back of like 1.5, hopefully, or somewhere.
Okay.
Yeah. So now,
Okay, gotcha.
sorry about that. Now we're on a specific page. So now we're back on 1.5 where we left off yesterday. Everyone with me, I hope? Okay, so we're going to define core electrons. We're going to define valence electrons. I'll talk about valence electrons a little bit, and then we'll call it a day in like 5 minutes or so, okay? All right, core electrons. These are the inner electrons. Oops, I can't spell. Okay, the inner electrons. That's an awful definition because the word core is obviously implying inner. Fear not, the next definition will make way more sense, and I'll come back to core in just a second, okay? But these are the inner ones, the ones closer to the nucleus, all right? Those are considered core electrons. Valence electrons are the exact opposite. These are the outer electrons. But let me be more specific than that. For our purposes, we can define valence electrons as the highest energy level S and P electrons. okay? These are the highest energy level S and P electrons. These are what we call valence electrons, okay? Now, the reason why this is important, or the reason why this matters, is because the valence electrons are the ones that are reacting, okay? These are the reactive electrons. When something is happening in chemistry, when a chemical reaction occurs, when electrons are shared, when electrons are transferred, the valence electrons are what's doing the stuff, okay? The valence electrons are what's being transferred. The valence electrons are what's being shared. The core electrons are just kind of sitting there, not doing a darn thing, okay? So when we talk about chemistry and we look at the electrons and what they're doing, what we care about or what we're focusing in on is always the valence electrons. These are the ones that are gonna make the chemistry happen, so to speak, okay? So let me go back to our first two examples and just kind of point out the valence electrons. The definition I gave you is valence. These are the highest energy level S and P electrons. So let's look at sulfide, the bottom one. Sulfide hits energy level 3. That's as high as it goes. So 3 is the highest energy level we reach. And I have 2 electrons in the 3s, and I have 6 electrons in the 3p. These 8 are for my sulfide. The 8 right here. These are the valence electrons. These are the outer electrons of sulfide. The highest energy level, in this case, 3, S and P electrons. These are my valence. The other guys, these are core. Okay? Everything else that came before it is a core electron. The highest energy level S and P are valence. So if I went back to the first example with krypton, you'll notice that the highest energy level we reached was 4. 4s and 4p are going to be the valence electrons. 3d is not valence. Even though it's between the 4s and the 4p in our electron configuration, they are not considered valence. D orbital electrons, or electrons that are in d orbitals, never are considered valence. Never, ever. Okay? It's only S and P. And it's got to be the highest level S and P. All right. I'm almost done, I promise. All right, last thing that I want to go through. I think it's the last thing. Second to last thing. All right. To find the valence electrons of any element, it's pretty easy. What we want to look at is, there's my periodic table. We want to look at the column of where that element comes from. On our AP periodic table, you have column 1, 2, and then we have 3 through 12, which are the transition metals. We're going to ignore 3 through 12. The transition metals don't really matter in chemistry until you get to like your junior year in college. I still hardly learned a darn thing about the transition metals all throughout my college as a chemistry major, okay? They're weird, they're tough to explain, so we kind of ignore them for a long time until you get enough chemistry that you can start maybe making sense of them. So let's ignore columns 3 through 12. And then we have columns 13 through 18. On some periodic tables, these are actually columns 3 through 8. And I'm going to use them as columns 3 through 8 for the next part, okay? If you want to figure out how many valence electrons something has, you look at the column number. That's it. If it's the first column, it has 1. If it's the second column, it has 2 valence electrons. If it's the 5th column or the 15th column on your periodic table, it has 5. If it's the 17th column, it has 7, okay? So it's just the column number. That's it. So with that in mind, carbon is going to have 4. If I find it on the periodic table, On your AP periodic table, it says it's in column 14. But again, we can look at the ones place of that, or if you ignore all the transition metals, it sometimes is called column 4. It has 4 valence electrons. Magnesium, that's in column 2. It has 2 valence electrons. Sulfur, that's in column 16 or column 6. It has 6. Iodine, that's in column 17 or 7, depends on the periodic table. It has 7. Aluminum has 3. Nitrogen has 5. Argon has 8. And lithium has 1. All I am doing is finding the element, matching the column number, and that's how many valence electrons these things have. Okay? Pretty simple, I hope. We'll need that moving forward. And it shouldn't be too bad to find the total number of valence electrons as we go. Last thing, and then I'll shut up and we'll call it a day. When chemical reactions occur, it is the electrons of atoms that are undergoing some sort of change, okay? When we talk about chemistry, we're generally talking about electrons doing something. Transferring, sharing, being lost, being gained, something with the electrons, okay? Sometimes electrons are being shared, sometimes they're being transferred, like I just said. Whenever the changes in electrons occur, it is always going to be the valence electrons involved in these changes, all right? It's the valence electrons that are doing the chemistry. That's all I have. I know that was rather dense, but I'm hopeful that my pace was slow enough that maybe you were making some sense of the last couple days. If you have questions, please hang around. I'm more than happy to chill for a little bit and help you out for the next half hour if you need it. Homework topic 2, again, is due on Monday. Homework topic 3 is due next week, Thursday. Tomorrow, you absolutely 100% have stuff to do for my class. Tomorrow, jump on It's Learning. I will have a video of a lab, and I'm going to ask you guys to fill out a quick little lab sheet, which I'll go through in its entirety on the video, and you'll post your work as a part of tomorrow's class. Okay? So no homework for tonight. There is stuff for tomorrow, but you should be able to do it during class with me tomorrow as a part of that video. Topic 2 is due Monday. Topic 3 is due Thursday. AP Classroom is dead until further notice. And that's all I have. Have a lovely day. Thanks for hanging with me. If you need help, hang out some more and we'll help you out.